The title is Life Cycle Cost Analysis of Alternative RC Bridge Decks.
So there's about 600,000 public vehicular bridges in the U.S., and of those, about 9% are rated structurally deficient, and that means there's an element, one or more elements had a rating of poor, 4 out of 9 or less. And so poor condition could be to advanced corrosion or deterioration or cracking, and some other effects as well. But these are often due to deck deterioration and caused by reinforcing corrosion. And here are a couple of pictures of actual bridge decks. In Michigan, I'm from there. In fact, I live about a mile away from ACI headquarters in Farmington Hills. And unfortunately, things haven't improved since then in that state. Infrastructure is very bad. I'm sure other places it is as well. So this is a real problem. And in fact, over 20 years ago, FHWA estimated $8 billion to repair damage to infrastructure just from reinforcement corrosion. And I'm sure it's much, much greater now. And various options have been proposed to replace bridge decks with more durable materials. We had an excellent talk earlier today just about that. New concrete technologies as well as new reinforcement types could be used. One drawback of these technologies is that they're often more expensive initially than a traditional bridge deck. And what I mean by traditional deck is just a normal concrete and an unprotected or black steel. And so we often use a life cycle cost analysis to evaluate whether or not these alternatives are competitive during the long-term life cycle of the bridge. One significant concern with this type of analysis is that there are a large number of uncertainties. There's uncertainties in the costs of these materials and the labor to install them. There's uncertainties in the maintenance scheduling for these alternative technologies as well. Now, there has been some research on this over the years, in the last decade or two, but most of these studies typically only compare one alternative to a baseline being the normal concrete and unprotected steel. And each study uses different assumptions with regard to costs of the baseline as well as the alternatives, and they also use different assumptions in terms of the activity timing for the maintenance scheduling. And moreover, there's a large degree of variation with regard to how uncertainties are considered in these costs. Some treat the process completely as deterministic. Some randomize some parameters to account for some uncertainties, say in costs. Some have considered time of the activity to be a random parameter as well. So lots of different variation in how these studies were done. And that makes the comparison very difficult to do. So the objective of this study was to conduct a consistent life cycle cost analysis of the multiple bridge deck options that are available, considering uncertainties as well in a consistent way. The bridges that we considered were very typical, one of the most common geometries and types in Michigan, and I'm sure as in other states as well. Two-span, a continuous bridge, we call this live load continuous, with a 2 lanes and 9-inch reinforced concrete deck. And here we just looked at AASHTO type girders as well as box beam girders. For the alternatives that we considered, certainly there's a large number of possible alternative technologies, but we had to limit our study just to where we had data available in the literature, data for costs and data for a maintenance schedule, a timing of the repair activities. So for reinforcement options, we had unprotected steel, epoxy-coated steel, stainless steel, and carbon fiber. Then for the concrete options, of course, we have normal concrete, one of various high-performance concrete mix designs, and internally cured HPC mix. And the advantage to this was, it was reported that this internal curing process helped to reduce the early shrinkage cracks, creating a less porous or a less permeable mix to prevent the waters and chlorides from penetrating to the steel. And then finally, there was one reported, it was an engineered cementitious composite link slab. And the idea here was that rather than have an expansion joint, so in the bridge we often have an expansion joint over the central pier there, and of course it deteriorates over time and water leaks down in that crack and then begins to saturate the ends of the girders and causes corrosion of the girder steel. So the idea behind this link slab was to remove that expansion joint and replace about 10 feet or so of the slab itself with very highly ductile, high tensile strength concrete. The drawback is it's very, very expensive. So for the LCCA model, first, for all the alternatives, the idea was we had to have a maintenance schedule such that they all allow the bridge to have a consistent condition, which was serviceable, and would be the same from one year to the next. And as I mentioned, the source studies, the studies that we pull this information from, they have different assumptions for the activity timing as well as for their baseline cost. And for the baseline, I mean just normal concrete and unprotected steel. And they also have different assumptions for the alternatives. So to consistently compare the timing and costs in our study, first we establish a baseline. And this is taken as the Michigan DOT baseline in terms of the cost, as well as the activity timing for the maintenance items. Then the timing and cost of the alternative construction was proportioned to the MDOT baseline based on the ratio of alternative to baseline reported by the source. And this allowed us to generate an equivalent MDOT value for the alternative construction cost or baseline activity timing. Now, the MDOT schedule assumes a fairly aggressive environment. There are a large number of freeze-thaw cycles, as well as a heavy use of de-icing chemicals. But there are a large number of major service activities. Initial construction, for unprotected steel, we have the cathodic protection, deck patching, overlay replacement, beam end repair and replacement, and then finally superstructure demolition and replacement. And this schedule shows well, first on the very left would be the baseline, the Michigan baseline for unprotected steel and normal concrete. Then the next would be epoxy coated bars, ECR, stainless steel, CFRP bars, the HPC mix that we had data for, the internally cured HPC mix, and then the engineered cementitious composite link slab. Now keep in mind that these scheduled activities are deterministic. In other words, the assumption is on the schedule, these activities will occur at these specific years. And that's clearly not realistic. One bridge is going to deteriorate at a faster or slower rate than another. So we have to consider those uncertainties. So not only in those timing activities, but costs as well. So we assigned the major timing maintenance activities as random variables, and the mean value of those, in other words, the average time that activity would occur, varies depending on what type of construction alternative was considered. And then we also put limits in the simulation such that one activity wouldn't occur too close to another and generate an unrealistic scenario. For example, we wouldn't allow, say, a deck replacement to occur one year and then the superstructure replacement to occur the following year. We also have uncertainties associated with the agency costs, the DOT costs, the materials themselves, the labor to install the decks, and the equipment used to install those decks. So all those major costs are also assigned random variables. And then finally, we have the cost to the user, the traveling public over the bridge because of the delays due to the construction. And these are a function of three major costs: the time travel increases, the vehicle operating costs, as well as the potential for increased crashes that would occur during construction. And these are a function of various parameters themselves: the length of the effective roadway, the number of days it would take for the maintenance activity to complete, the volume of traffic over the bridge and under the bridge, and so on. And then from these parameters, we could generate user cost random variables as well for the major construction and maintenance activities. So we used a Monte Carlo process to look at how these uncertainties could be incorporated and understand the probabilities that one alternative may cost more or less than the baseline. So I'll walk you through one simulation. In the process, it would work like this. First, a lifetime maintenance schedule was generated based on the activity timing random variables. Next, for each year, the random variable costs are simulated, converted to present value, and then summed. These two steps are then repeated for each construction alternative that we had. Next, we formed a cost limit state function in terms of the difference between the baseline and the construction alternative. So clearly, if you look at that function, if it's less than 0, the alternative is less expensive than the baseline. And we repeat these steps 1 through 4 for about 100,000 simulations, and that gives us enough data to compute the probabilities that the alternative was less than the baseline. We did this for a number of scenarios. I'll show you one here as an example. This is for an AASHTO beam bridge, high traffic volume on and below the bridge. Now, the traffic volume didn't affect any of the maintenance scheduling according to any of the literature that we could find, surprisingly enough. But what it did do is, in our analysis, it affected the user costs. The higher the traffic volume, the more traffic is delayed and so on, and the more cost to the public. So what this graph shows is the vertical axis is a probability of the alternative being less than the baseline as a function of bridge year. And as you can see, some of these, mostly towards the bottom there, have a probability less than 0.5 or lower than 50%. In other words, it's likely they're going to cost more than the baseline. But some of our cases actually had, for the initial construction, a higher probability than 0.5 of costing less than the baseline. Now, the reason for that is the use of epoxy-coated bars in place of unprotected steel. The unprotected steel, at least with Michigan DOT, is associated with cathodic protection system, and that's a significant initial cost of the bridge. When you eliminate that cost, that causes those probabilities to change quite significantly in some cases. In all of these cases that we looked at, however, it's very clear that as time increases, they become more competitive. And in fact, towards the lifetime of the bridge, some of them are extremely likely, 99% or higher, to cost less. Now, kind of to summarize some of the information on that table, first, we have in the very first column at year 0, it shows some of these probabilities that the alternative, shown in the very left column, will cost less than the baseline. So all of the upper 4 options there, ECR, the epoxy-coated rebar, all of those, as can be seen, have a likelihood of costing less during the initial construction than the unprotected steel and normal concrete. The ones that are, even the ones that are more expensive initially, shown on the lower 5 there, all of them seem to appear that they're going to not be too far away from 50%. In other words, even at the very most expensive one, that black steel or unprotected steel and the engineered cementitious composite link spam, it's only a 35% chance to cost less than the normal steel and the normal concrete option. The second column there, the year that probability is at least 0.5, that's essentially the break-even year. In other words, when do we expect each of these options to have a equal likelihood to cost less or more than the baseline? And as you can see, almost all of them there expect to break even by about 6 years from the initial construction. And only a couple options there, the ECC link slab and the stainless steel bars, take a little bit longer to break even at 11 and 14 years, respectively. By year 25, the most effective options in terms of probability to cost less are the normal concrete and epoxy-coated bars, shown at the very top at 97%, and the CFRP bars and the normal concrete also at 97% near the bottom. By year 50, all the options except for 2 have greater than a 99% chance to cost less. Now, if you look at the entire life cycle of the bridge from year 0 all the way to 75, from this information that we have available, it appears that a very common option, this epoxy-coated bar and normal concrete, appears to be a very good option. It initially costs less, has the highest probability of costing less of these options, and it stays very high to cost less throughout the entire life cycle. Now, that said, this is based on the information that we could find in the literature. We didn't question the assumptions in terms of the maintenance scheduling or the cost proportions. And that's going to vary, of course, tremendously depending on where you are. One state or contractor is going to have a much different cost ratio from one of these alternatives to the baseline based on their experience level and so on. So this is, I think, is a good general guide, but these numbers would have to be massaged to be more locally specific. And that's all I have. Thank you.